Hi, and welcome to my channel, JaberTime. Today we're going to talk about domain and range, piecewise functions, and some examples. You could see from this graph right here that the domain will be the inputs, the range will be the outputs, and the function is the function machine that tells you how to go from A to B. For example, if the function says 2x, that means the function machine, anything I give you, you have to multiply it by 2, you have to double it. If I give you 5, you multiply by 2, you do some work, and you give me the output, which is 10. 5 times 2 is 10. The domain will be coming from the inputs, and the inputs will be usually x, and the range will be coming from the output, which is usually the y as a graph or as a function. So in this graph, it starts right here. As you could see, it doesn't have an arrow like this side. So the domain starts from here. And since the graph keeps going, I know you feel like it's going down, but it's not moving right a little much, but it is. So the domain will be from this point all the way up. And the range, because it doesn't pass this point going up and comes from the y values, the range will be from this point all the way down. This is the graph that I'm talking about when I describe piecewise functions. Okay, let's see some examples. Find the domain and range of this set of order pair. We just mentioned that the domain is x values, the inputs, and the range is the output values. So we're not giving a graph, we're giving some data, some values. The domain will be the x values, and I could see the 2 and the 3 and the 4 and the 5 and the 6. So that's my domain. It's a set of these numbers. The range will be the y values, but look, 10 is repeating. I don't have to repeat it here. In set notations, we don't repeat numbers. So the range has only 4 numbers, where the domain has 5 numbers. Here's a graph, and as a graph, and using also algebraic expressions or solving using algebra to find the domain. From the graph, I could see that x values start from -4 to the right. The y values starts from the level down here all the way up, so from level 0, looking at the y values. Let's move it to the left so I could show you some work, or move the graph. Same graph, same question. The domain will be x greater than or equal to -4, so from -4 and up equal -4 also, with the equal sign. As set notations, or sorry, interval notations, it's from -4 to infinity, and we can't include infinity because infinity is not a number. It's just like, it's a direction, it's a behavior. Using algebra, this is my function f of x equals 2 multiplied by square root of x plus 4, but we know that we have restrictions. We always pay attention to restrictions when you have square roots or you have fractions. You can't have negatives inside square roots. You can't have negatives inside square roots. You can't have zeros in the denominator. So if the square root also is in the denominator, you can't have 0 and you can't have negative, so it has to be positive only. In this case, yes, I could have 0. So I'm saying x plus 4, which is inside, could be 0, but has to be positive also, not negative. So it's greater than or equal to 0, but not less than 0. Subtract 4 from both sides, I get x greater than or equal to -4, which agrees what we saw on the graph. It's from -4, including -4, and up. Here's the range. The range is y greater than or equal to 0. So it's from 0 also all the way up. As you can see, it keeps going from 0 to infinity. Algebraically, this is my square root, and I'm multiplying by 2, so it's going to go faster by 2. Square root of x plus 4 is always greater than or equal to 0. Could be 0 if x is negative 4, of course. And that's why it's right here. Multiply by 2, it's gonna still be greater than or equal to 0. So the range is y greater than or equal to 0, or from 0 to infinity. Here's some notations. I'm not going to read all this right here, but you could pause the video and look at it as notes. But I'm going to talk about some in the coming slides. X is greater than a. That means from a all the way up, not including a. X is greater than a. That's how we read it. For example, let's see this one right here. A is less than or equal to x less than b. We read it actually differently by saying x is greater than or equal to a, or equal to a with closed brackets, and less than b. Close brackets at a, open at b, because it's less than, it doesn't have the equal sign. That's how we graph it, and that's how we say it. X is between a and b to include a, or I would say we say x is greater than or equal to a, less than b, and less than b. Okay, let's move on. Well, this right here, everything is belonging to you. It's kind of hard to see a graph here of blue, but what they are saying, we are taking 2 out. Open circle, that means this point is out, it doesn't belong to you. You can't, a point does not have a size, so we can't just like mark it in such a way that tell you that it's out till we make it large enough for the view to see it. So this number line is telling you that everything is yours except this point. So x is less than 2 or x greater than 2. You could be here, you could be here, but you can't be at both sides at the same time, and that's why they're using the or. Differently, you could say it's from negative infinity to 2, union from 2 to infinity, not including 2 either way. And that's what we have. Now, graphically, this says all points from 5 to 10, not including 5, including 10. H is greater than 5, less than or equal to 10. Or as a set builder notation, this is inequality, this is set builder notation, you could say H such that this vertical line, sometimes we use a forward slash, means such that H is greater than 5. As you can see, not including 5, 5 is out, it's an open circle, and less than or equal to 10, including 10 also, it's solid dot filled. As interval notation, it's from 5 to 10, not including 5, including 10. And the rest are more examples. And let's see some individual ones one by one. This is from 5 to 10, the one that I just mentioned. This is from 5 to 10, but not including 5 and not including 10. That should be clear. Not including 5 and not including 10. All right? No equal signs. This one is from 10 all the way down, but not including 10. So h is less than 10. H such that h is less than 10 as a set notation. From negative infinity to 10, open, open. This one from 10 up, including 10. H is greater than or equal to 10. And brackets about 10. All the way to infinity. Infinity, of course, every time we use infinity, we can't use brackets. This is all the way to the left, all the way to the right. That means all real numbers, all real numbers. And we write it from negative infinity to infinity. This one here, as a set, says x such that, I know it's kind of like a little bit confusing with double lines, but this line is such that, and these two lines means absolute value of x, such that the absolute value of x is greater than or equal to 3. That means from negative infinity to negative 3, if you solve it, union from 3 to infinity, including 3, including negative 3. If you go back to 2 videos before this one about inequalities, we talked about inequalities and solving inequalities. Whenever you say greater than, you have two options, and we use the word or. Either you go up or below, and if you have less than, you are in between, which is 2 videos before this one. I'll put the link at the end of the video, and I'll put the link in the description if you want to see more about inequalities and solving. Here's a graph that describes a solution. So you are going from 1 to 3, including 1, including 3, and above 5, more than 5, but not including 5. As an inequality, we say x is greater than or equal to 1, less than or equal to 3, or, because you can't be here and here, x is greater than 5. As a set builder notation, we say x such that x is greater than, it's the same thing, but we just add those set notations and add x in the front. As an interval notation, we say from 1 to 3, including 1, including 3, union from 5 all the way to infinity, but not including 5. And the graph shows it and says it. One more time, here's domain and range. We talked about domain and range on the front slide, the first slide. The domain is x values that belongs to your graph, if it's a graph, and the range is the y values that belongs to the graph. We're starting from this point down, and we're starting from this point to the right. Here's an example. What's a domain and what's a range? Well, I think the domain is this way, and the range is this way. So that's a domain, and that's the range. And to describe more, the domain would be from this point to this point, including this point, including 1, because we're looking at x values, and not including -3. So here's a domain. From -3 to 1, including 1, and not including -3. How about the range? The range is from this point down here, but this point is not included, but it's covered here. So the y value 0 is still part of the range, yes, all the way down to -4. So from -4 to 0, wouldn't say from 0 to -4, and the proper way is from a to b, where a is less than b, from -4 to 0 on the y values. Here's some notes, if you want to call it, and you could slow down the video if you want to see more or read more. But I'm going to go fast, a little bit fast, to save some time from recording. But at least you'll have notes and you have some knowledge about functions and domain and range. Here we go. This is a constant function. You could pause the video by hitting the space bar and read this, and after that hit the space bar again, it will play. But I'm not gonna be reading all this, there's no need. It's just a reference for you. A constant function has a domain of all real numbers because it's x, and the range is only from c to c, or just c. Alright, this is the y equals x, or f of x equals x. We talked about that, the identity function, in the previous video. The domain is all real numbers, and the range is all real numbers. You could see it right here. From -infinity to +infinity is another way to say it. As you can see, I'm going a little bit fast, but it doesn't hurt to see enough examples, the major examples that everybody should know and be aware of, which helps a lot. So this is the absolute value function. The domain is all real numbers. It goes all the way left, all the way right, but the range is from 0 up, so it's from 0 to infinity, including 0. This is the quadratic function, y equals x to the second, the basic function. Domain is all real numbers, and range is from 0 up to infinity. This is the cubic function, all real numbers for domain, all real numbers for range. This is 1 over x, as you can see right here. Of course, we can't use x in the denominator, which I mentioned earlier, so it's taken out of the domain. The domain cannot have a 0, which means also the y value is not going to be there to correspond to that location, x equals 0. So the domain is from -infinity to 0, not including 0, union from 0 to infinity, not including infinity, and they're stated right here. Same thing happens for the range going from negative infinity to infinity, but taking the 0 out. This is 1 over x to the second from the previous video. The domain is all real numbers except 0, because you can't plug in 0 in the denominator. And the range will be from 0 up, not including 0. Domain from 0 to infinity, that's the square root of x. You could have 0 here. Square root of 0 is 0, but you can't have negatives, so it's going to be from 0 to infinity. Range will be also from 0 to infinity, which is stated right here to speed up the process and save you some time. This is the cubic root of x. Domain is all real numbers and range is all real numbers, or differently, that's how we write it down. Here's my last part, which is the piecewise function. It's a function made of pieces. This is the piecewise function. As an example, x to the second if you are less than or equal to 1. 3 if x is greater than 1, less than or equal to 2. And I don't know if I said x. 3 if x is greater than 1 or less than or equal to 2. X if x is to the right of 2. Let's take one by one, piece by piece. Here's the first piece for x to the second being to the left, including 1. So if you graph it, it goes all the way, but we need to stop right here and include 1 because 1 is part of the game. 1 square is 1, so that is going with this condition 100%. Now this is a horizontal line. It's a constant function. Y equals 3, but you are between 1 and 2, where 1 is not included and 2 is included. So you're going to go up to 3, up to 3. This is 3 right here. And you're going to be between 1 and 2, including 2, but not including 1. And that's what I meant. All right. This one is y equals x, the 45-degree line, the identity function. And you're supposed to be to the right of 2 only. So at 2 output, it's going to be an open circle. 2 will give you 2, but I'm not going to be there. I'm going to have an open circle right here. Instead of graphing y equals x going through the origin, I'm going to start here and be only to the right side. And that's what I mean. Now putting them all together, that is the piecewise function being graphed. That should do it for this video. And I did my best not to make it half an hour or more. And hopefully it was helpful. Thank you. I'll see you in the next one. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.